Hi everyone, welcome back to the Quantum Mechanics for Everyone video series. So this is the fifth episode of this video series. If you have not watched any of my videos yet, I strongly encourage you to go through all of my videos, as most of the prerequisite knowledge is there in my previous videos. In today's video, I'm going to uh, lock most important concept, the most important picture, quantum picture in your mind. So you have to be patient and carefully watch everything that I'm going to teach you today, guys, as uh, this picture matters the most. So what I have noticed so far in my life, in my teaching career, in my educational career, is the students are unable to properly imagine what exactly, or intuitive picture uh, is quite weak, so that they can't imagine what exactly quantum world look like. So I'm going to just change this picture today, guys, and I'm going to draw a picture gradually. This is going to be a real piece of art, so you have to patiently watch the video till the end of the video, right? The real game changer is there are four observations that classical physics guys mainly, not four, there are more, some other explanations, very so many observations that classical physics actually fails to explain, guys. Even though classical physics is a powerful tool, some of the observations in physics can't be explained using this powerful classical physics tool, so we need to have something else. Another tool is required, so that tool is quantum mechanics. So let me introduce few things, but guys, I'm going to quickly walk over these experiments, as these are not my uh, my major experiment, that I'm going to simply refer to one of the powerful experiments. So and I'm going to extend that experiment to the simply math, and then you'll be able to see the exact picture later. And third one is not even been mentioned here so far. So, but let me quickly go over these experiments, guys. These three experiments, I'm not going to dive deeper into these things, as most of these videos are there. You can even find out, and I'm going to put some links to in my description. You can go through these links and watch. If you are very interested in these observations, these experiments, you can learn more about them in these videos. Everything's been properly mentioned, right? So, but here, number one is photoelectric effect, guys. You already know what photoelectric effect is. Most of you guys know what photoelectric effect is. Those who have already studied physics in the high school level, they must have already encountered this experiment, right? So what we do here is, and simply if I explain here, if you shine light onto this metal piece, this is a metal piece, guys, and regardless the intensity, right, regardless the intensity, if you increase the frequency, yeah, some electrons are emitted at a certain instant, at a certain particular frequency, and then if you increase the frequency more and more and more, regardless the intensity, the kinetic energy goes up. Kinetic energy of the electrons goes up. This is a bizarre observation, guys. Classically, you can't explain this. The problem with the classical physics is, the classical physics uh, yeah, strongly believes that when you when you keep the intensity of the light beam constant, the energy falls onto this surface remains constant, so that the energy of electrons can't change. So uh, this observation failed that classical point of view. So we can't use this method to explain classical physics, to explain the the exact mechanism that we can observe here, right? And the second important thing is ultraviolet catastrophe, guys. So the problem with ultraviolet catastrophe is a black body. So you already, sometimes you might have heard of black bodies. If you don't know really think anything about black bodies, guys, it doesn't matter, because black body is an idealization. Black bodies do not really exist, but just imagine for a moment, a star is, the stars or our sun is almost like a black body. A blackbody is a particular object or a material who can absorb every single radiation and who can emit every single radiation, right? And here the even black bodies, if depends their radiation, the emitted radiation depends on their temperature, guys. When you increase the temperature more and more and more, the wavelength of the radiation decreases more. So that classically, if you just classical theories, if you use to just derive something about this energy, you will end up with something like this, guys. So this is called the Rayleigh-Jean experiments or Rayleigh-Jean methods. There are Rayleigh-Jean observations or explanations. If you try to apply to this exact observation, guys, we end up with something like that. But this blue color picture shows the real picture of this one, or real experimental observation. So if we experimentally try to find what it looks like, this is what it really looks like. So then they simply, this one doesn't really explain what's really going on here, right? So you can't use classical physics to explain this one, guys. Even this is another very a complete lesson is required to explain exact picture of this one, but I'm going to just put a link. You can go through that one and watch what exactly this explanation is. And the next important thing is the electron energy level, guys. So now you already know that electrons are orbiting the nucleus, but the problem is we already know that charged particles, when you accelerate charged particles, right, when you somehow manage to accelerate them, guys, they emit electromagnetic radiation. Simply they emit some energy from them. So they emit energy. Their energy is released by these electrons or any charged particle. But here we already know that when something is moving around a circle, they change their velocity continuously. So theoretically or technically there's an acceleration on this one, right? So technically there's an acceleration on this one, so that these electrons are supposed to release some energy to the environment. So as a result of that, they should slow down as they reduce their kinetic energy. So they should spiral into the nucleus. So nothing like that happens in reality, guys. Even this is a very weird observation, a bizarre one that you can't explain. On top of that, electrons usually stay in these energy levels. They don't, for example, these electrons exist at various energy levels, so they jump from one to another, but they don't ever stay in between. Why can't they really ever stay in between? So we can't classically explain this, guys. We can't classically explain this. That's not the biggest, or one of the biggest rival of classical physics, as classical physics completely fails to explain this observation. So apart from these observations, the game changer is the double slit experiment. So I erase all of these things, guys, as these are very important experimental observations, but they don't really help us to understand the quantum picture of a particle. So I'm going to draw that quantum picture of the particle in your mind. So listen to me very carefully, guys. Right. Now, imagine for a moment the double slit experiment is something like this. Right. Put the double slit experiment aside. I'm going to draw two experimental setups. Right. Imagine you have two slits. You keep two slits like this, and there's a sniper here. So we place a sniper gun, and there's a screen over here. And this is the screen here, and here we have a wave generator here. Right, that's the second case. two different stories, and you have another yes, two slits, and this is my slit number 1, slit number 2, and there's another slit number 1 here, slit number 2, two different stories, right? And you place another screen like this, right? And imagine those are not just screens, they can just detect whatever whatever they touch can be detected by these screens. So those are very sensitive screens. For a moment, just imagine, right? So now guys, if you just shoot electrons, or not electrons, my bad, just bullets, right, at the screen, imagine these bullets can somehow go through these slits and just made the screen at this point. So if you continuously let these bullets go through these slits over time, right, so a clump will appear like this. And simply imagine if these pulses represent the intensity of number of bullets here, you'll be able to see electrons like this. There are electrons, so many electrons like that, right? So there's no problem with that, because this is the point which is exactly in front of this slit, and this is the other point which is exactly in front of this slit. So it's totally fine. We can find so many bullets exactly behind this slit and behind that slit. Right, now my wave story. Now imagine if you have, right, yeah, this is my wave generator. Right, so now this one generates waves like this, and you let them go through these two slits. We already know that because of the obstruction here. So there will be another, these two will act as two another wave wave generators. Now they will create two waves, and these two waves will just, right, these two waves will just interfere, and as a result of that, the interference patterns will be formed. So if you carefully observe the screen will show you that interference patterns like this, right? So intensities vary like that, right? At some points the intensity goes to 0, at some points intensity goes to maximum. So this is what exactly the final intensity of the waves look like, right? But now this is the game changer, guys. What if you perform the same experiment with electrons? Listen to me very carefully, guys. Something very, very weird is going to be observed. What is that? Now, just erase this one, as this is way more important, guys. Right? Same experimental setup. Now, you have an electron gun like this. Instead of sniper, you are going to replace that sniper by a gun which is now this time shoot electrons, right? Now two slits are still here, right? And this is the screen. I'll give you a second, think for a moment. What will you observe in this case? Even physicists expected to see a clump here and here the same as that. So they expect electron to gather exactly in front of this slit, slit 1, as slit, this is slit number 2, as this is a perfect particle. Electron is a perfect particle, and even it's a part of our particle model. If you're someone who's mastering the particle model or particle physics, you already know that electron is a perfect particle. So we expect electrons to just gather exactly at a point which is exactly in front of slit 2 and slit 1. But miraculously, electrons start, so even if you send one electron at a time, guys, they exactly land at some selected points, and they avoid some points. They never even look at those points. So what we can observe is, again, a pattern like this, an interference pattern. This is a game changer, guys. Uh, this is a very, very powerful experimental observation that even the classical physics, that classical world was completely shattered by this experiment. Right? Right? Because this observation shows that electrons, for some reason, they avoid some places. Right? Like they have predetermined that we are going to just land on these places and we completely avoid other places. This is very strange. Right? This is not over yet. So I'm going to make it more and more strange, guys. What if now, and even physicists were wondered by seeing this, guys. Nobody was expecting this, right? And the physics world had not been ready for this, right? But then they really wanted to see, oh, if something like that can happen, what if uh, through which slit exactly these electrons now, uh, electrons land on each places, so they really wanted to check through which slit at each and every moment an electron goes through. So in order to find this out, what they did was, right, so they placed, right, I'm going to draw it onto the side of the, I need some space, right? So what they did was they modified this setup a bit. Again, one electron at a time. This time, same double slits, nothing has changed, same screen, but they place two detectors exactly uh, near these. So these are two detectors, another detector to see through which slit this electron passes through at each and every instant, at each and every moment. Believe me or not, another miraculous observation was observed. A very fascinating observation that single-handedly shattered the physics world, guys. What is it? They observed that even this time, these electrons out of nowhere started to behave as particles. This time, they just again make clumps exactly in front of these slits, just as our bullets. So they behave as waves when you don't observe or don't just bother those electrons or don't just detect them. Sorry, yeah. And then when you detect, as soon as you start to detect these electrons, they start to behave as particles or simply like those knife bullets. This can't be observed by, this is very strange, right? But then the physics world really wanted to describe this model, guys. So there are so many physicists, uh, Schrodinger and Heisenberg and even Albert Einstein up to some extent, because he was a bit against with quantum, but so many physicists contributed, and they realize the reality is not exactly what we see, guys. Right? People had believed that reality is what we always see around us, but they realized that reality is something far beyond that. If you want to describe this, if you really want to feel the reality, we need to have something else, right? So they introduce something called the wave function, right? So now let me introduce what exactly the wave function is. Now it's high time, actually it's the right time for us to understand what the wave function is, right? Now in quantum mechanics, guys, uh, particle is, sorry, the electron or anything is not a particle nor a wave unless you observe it, unless you measure it, unless you detect that. It's just a wave function which some sort of information are stored in the wave function. So wave function evolves, wave function just travels, and it brings some information, right? So the wave functions, and you can't exactly, now wave function is still a very mysterious thing, because you can't even Schrodinger himself said that. He introduced the wave function, but he himself said that even I can't understand what exactly the wave function is. But instead of that, he said that, but wave functions, for example xt or x, you can choose depending on the context, but if you get the square of this one, this has a meaning, right? So this has a meaning, as this one explains the probability density of the particle, in the sense probability density is probabilistic, right? So where we can exactly find a particle, right? So then, for example, if you have a probability density like this xt's, and if you get the square, if you know the wave function, and if you get the square of that one, imagine if you end up with something like that. So this means that you can find the particle. This is x, imagine for example this is a position, so you can find the particle move at a. It doesn't really mean that always you can find the particle at a. That is the probability, highest probability of finding a particle at a. And you can clearly see that here. If, let me take this b and c, beyond c you are strongly you are totally capable of telling that particle can't be ever found beyond c, or here behind the b, because wave or the density or the probability density is 0 here in this region and here in this region, right? So this is the simplest way to view this, guys. But now how can we explain what we have just observed using this same model, right? That's my next objective, right? So what, right? So what they said was, now imagine, right, let's try to model the same experiment again. You send an electron, unless it is observed, unless it is measured, there's no electron. There's no electron at all. There are two slits. There is just a wave function. So wave function is like a cloud, but I don't like to use this cloud term, because most of the time students try to imagine it as a cloud, but it's not a cloud. It's some sort of information. That some sort of probabilistic information is carried by this wave function. Right, this is electron, but it is no longer an electron. It looks like a wave function, like this. So I'm not going to even put that xt stuff, right? So he's our friend, the wave function. But as soon as it reaches this height, this point, so wave function has two different uh, different paths that wave function can take any of these paths. Not really. The wave function don't take any of these paths. We already know that this is highly probabilistic, right? So wave function is now going to share or evolve, and one part of the wave function goes through this one, which is phi 1, and the second part of this wave function goes through this one. Now it is phi 2, right? So you can say that this phi is equal to phi 1 plus phi 2, and this is actually the phi represents the amplitude of this one, so that amplitude phi 1 plus phi 2, right? Now these two waves are again going to meet on this screen, and screen is waiting over there to measure, right? So as soon as they meet the screen, this is the same electron, guys, remember that. Even if you send one electron, right, so not many electrons this time, just a single electron. Weirdest thing is here is this one electron is going to just superpose with itself. How strong, how strange this is, right? So now this wave function is going to meet at each and every point, guys, right? And now we are going to make a decision here. So all we can do is, if you really want to find whether this electron, right, can be found at a point, can appear at a point or not, or how probabilistic it is, you can't straight away just you can't confidently say that electron could definitely be here. No, that word is over here, guys. That is the classical word. In classical world, certainty is the main tool, main inspiration. But here, uncertainty is the main inspiration, guys. Though you like it or not, you have to deal with that uncertainty here, right? So you already know that sometimes, even previously I tried to explain that these numbers are imaginary numbers, pi 1, pi 2, imaginary, right? Uh, they can even be real, but mostly imaginary. It doesn't matter. So now if you want to find more about wave function, and as I mentioned previously, guys, if you want to just feel something about this, and these wave functions, they carry just information, but even wave function itself is not just the probability, or it's not just the probability. So if you just want to find anything about probability density, you have to be smart. What you can do is you can just get the square of this one, right? And when you get square, guys, always remember that I'm going to just those are imaginary numbers, so phi squared will look like this, right? So let me use the other side. I think I need some space to draw this properly, right? So yeah, this space would be more than enough for me to just clarify this one, right? So then here, right, so now yeah, so let me write it like this on the other side. Now here, as those are imaginary numbers, guys, if you get the square of this one, right, make sure that you get the complex conjugate of this one, right? So those are not like our general numbers. We get the complex conjugate of this, like this, phi 1 star plus phi 2 star, right? And I'm going to later on, this is not the right time to prove this one, because in my next video I'm going to prove this, and I'm going to just explain, and I'm going to derive one of the powerful equations, which is Schrodinger's equation, right? So now when you get this one, guys, you will end up with something like this. So pi 1 star plus pi 2 star plus you have pi 1 pi 2 star plus pi 1 star, and here pi 2, right? So now here, guys, this is the pi 1 squared. Actually this is the mod x of that one. Mod represents the magnitude. So this is because we already know that pi squared is a magnitude, or simply it has a value. It describes the probability of this one. That's the probability density, right? So that this has a value. And even here, if you get pi 2, now here actually it's pi 2 squared that is a value, that's a real positive value, because when you multiply the phi 1 times phi 1 complex conjugate, when you end up with the magnitude of that one. But this is a bit strange, right? So now I can, later on I'm going to show you that even if you get this one, guys, we end up with a real one later on, because this is supposed to be real, as we expect a real answer at the end of the day. But it is real, don't worry, believe me. For now, I'm going to later on show that in my next video anyway. So here I'm going to put this real sign to represent, or when you add them together, actually they become same actually. So you can say pi 1 pi 2 star or something like that. These are same. You'll be able to later on see that there's no difference at all. But now you can clearly see that this real number, guys, these are anyway plus numbers, because we put mod. This is a plus number, anyway a plus value. This is a plus value, right? So now this one is the decider. This is the decider, because this one decides now where we exactly can find out the particle, or how probabilistic, or probabilistically how can we, how or the possibility of find a particle, how probabilistic the finding particle at a given point is decided by this very powerful term, guys, right? So even you can use I'm going to use electron. This is just a very surface way or surface view of this one. When you dive deeper into this one, guys, later on we'll be able to see that you have sine or cos terms here. We can use that to exactly show the interference patterns, or the nature of interference patterns can be viewed, can be observed by this one. So that is the big deal. Try to understand this one, guys. This is the game changer. This is a very important but question is, why don't we observe the same thing when we place these detectors? When we place detectors, as I mentioned previously, two clumps can be observed uh, just as a particle. Now electron starts to behave as a particle. It's no longer a wave. So what happened to the wave function? This is something very important. Quantum mechanical, we have to analyze what's really going on here, right? So let me explain what's exactly going on, guys. Quantum mechanics claims that as soon as you make a measurement, as soon as you observe the wave function, as soon as you try to detect that, the wave function collapses and it starts to appear as a particle itself. The collapse theory is a deep concept, guys. Even so I can talk about the collapse theory for days, but I'm not going to dive deeper into that collapse theory today. But here the wave function is going to collapse, so only remaining thing is now we already know that the wave function of the particle. So then here there was a wave function, and that wave function was shared among these two slits, and it was evolved, and now phi 1 part is detected by this one and phi 2 part is detected by this one. But don't ever forget, don't ever mess this up, don't ever screw up. Remember that, guys, this one represents the probability density, and this is already been observed. This is already been observed as soon as they pass through these slits, and then there is no longer a wave function. Wave function is no longer remaining to go through this one anymore, right? So then actually we can find, actually we detect where exactly the particle is at, right? So here the only remaining thing is now we can identify that here the probability of finding the particle at that point will be phi 1 squared, and probability of finding the particle at this point, or uh, probability of that electron is passing through this slit is phi 1 squared, and probability of that phi 2, or sorry, the electron passing through this second slit is phi 2 squared. And then that's all, guys. So there's no interference, no overlap, so the wave functions are collapsed here. at this point as we try to detect or observe them, right? So this is simply the quantum mechanics from scratch, guys. I explained. So understand that hereafter no interference, and then either you can see the particle, either the particle is going through this slit, or particle goes through this slit, and then they end up somewhere here or somewhere here.